Hello, everyone. Welcome back to the online causal inference seminar. I hope you all had a nice holiday break. We're very pleased to start this seminar series this year with a month of seminars about causal inference and fairness. And we're very fortunate to have Professor Ilya Shpitser from Johns Hopkins to kick off this seminar series. The discussant today will be Ricardo Silva from UCL, and the questions will be handled by In, and I'll give the mic to In to explain how this works.
Thank you, Qingyuan. So as usual, please submit your questions through the Q&A section. It is a button at the bottom of the Zoom window. Please do submit the questions to the Q&A instead of the chat for us to better follow. And without further ado, please feel free to get started.
Okay, thank you. So I guess I will share. Okay, thank you so much for inviting me. It's an honor to be here. Algorithmic fairness is such a huge exploding area right now. It's very difficult to give it justice, and I sort of got involved in it a while ago, and like many other people, because I've read ProPublica's article on machine bias, and it made me very angry. And I started sort of thinking about these issues, and I think now it's, there are conferences on fairness and so on, and I'll just discuss some of the stuff that we did. And I think it's not it's interesting. I started being very confused about how to think about fairness, and then I became very sure of myself. And I think now, as I'm giving this talk, I kind of went back to being confused, because I realized that fairness is such a complicated thing. There are many ways to approach it now, and the more I read it, the more I'm convinced that just how difficult this problem is. And the other thing I will say is that this talk is kind of a summary of lots of different approaches that are sort of related to thinking about fairness issues in a causal way. And so you see that there's a long list of people this is joint work with, because basically I was just going to be mentioning a bunch of different papers. Not all of them are directly about fairness, but hopefully all of them are related. Okay, so machine learning is becoming a commodity technology, of course. So everyone, it's becoming integrated in a lot of, business logic. It's being used in vehicles. It's being used in governments. ChatGPT came out, and now it's going to revolutionize education and, probably law and consulting and other things like that. So it's just becoming deployed very widely, and possibly is being deployed too quickly. And in particular, I think this kind of technology is being used to make influential decisions in people's lives. There are autonomous vehicles that potentially can hurt people. There are various predictions that are used for making influential decisions about medicine, about insurance, things like that. There are resume sorting algorithms that human resources uses, and universities also use to some extent. And there are well-publicized failures of those algorithms that I'm sure you've read about in the news. And the big thing that kind of got me started was a criminal justice system using these algorithms in various ways, in particular for helping judges make bail decisions and for sentencing. And a lot of these uses of data science, of machine learning methods, are based on complicated regression problems. Essentially, you have a very high-dimensional set of features, and you have an outcome, and you have some model parameters. And you learn it by minimizing some loss, and then that's surprisingly very useful in lots of domains. And of course, in classical regression models, there is nothing that's encoding corrections, possibly for discriminatory or unfair biases. And of course, as soon as you start worrying about that, like, are we using something like race or gender inappropriately in this model, then you start thinking about what it is that discrimination and fairness is anyways. And as I'm sure everybody on this call is aware, that's a big can of worms. And subsequently, how do we make statistical inference fair is a big can of worms as well. So there's lots of interest. So I wrote this particular slide a while ago, and it's only become more true, right? So there's lots of interest in fairness now from a variety of framework, and this interest has only increased. And I've read a lot of fairness papers in my day, and I still do. And a typical kind of machine learning paper on fairness looks like this. We will define discrimination as some red X. We will then propose a fancy mathematical method to correct for X, and we are now fair. And then we will have a data application and a simulation illustrating our fancy mathematical method for correcting for X. There are lots of X's because there are lots of fairness papers, and that trend is only going to increase. Now, my original critique was that very often in these papers, an analytical philosophy step is missing, which is an argument for why we should care about X by trying to tie it to some application or some example. This argument, I think, is less kind of pointed lately because I think many folks working on fairness are starting to take this step seriously. I just think that a lot of folks who work on fairness in data science just don't have the philosophy training to really address it properly. And of course, in analytic philosophy, there is a huge literature on related questions. People have been arguing about fairness for a very, very, very long time, certainly predating computers. And so broadly, there are two ways, there are possibly others, but there are two ways to judge quote unquote rightness. You could try to have a dialogue like Socrates, and essentially you propose an example, and then somebody shoots it down, and then you propose a fix, and on it goes like this. And ultimately it bottoms out in human intuition about examples. And so the one example that does this in the literature that I'm familiar with is token level causation. Like, what does it mean for one event to cause another? And if you've ever looked at this literature, there are these endless papers that argue about these preemption examples, like I'm crossing the desert and I have a canteen, and the canteen has water, but the water was poisoned, but somebody shot the canteen and the water fell out, and then I died. And then what event caused me to actually die? And so you could kind of go on and on like this forever, not necessarily converging to a resolution. And then there is a Euclidean argument. Euclid, of course, was a famous geometer, and this is all about axioms and principles that we think we want to satisfy. But still, you need some sort of suitability argument for your principle. Okay, so with that in mind, I'll talk a little bit about our approach, which certainly can be criticized. I think Ricardo will mention some things about that later. So we are worried about a sensitive feature and an outcome in our approach. Sensitive feature are the kinds of things that you can't discriminate against, like race or gender, sexual orientation, religious views, and things like that. And our approach, so I'm a causal inference person, of course, and our approach is inspired by causal inference. Now, I used to think that it was naturally right that we should think about fairness in this way. Having read so many fairness papers these days, I've quite moderated my approach. I think there is no one formalism that works for all problems, but I do think there are classes of examples where the kind of approach I'm going to talk about, I think, is quite natural. Now, in causal inference, what we do is we have factual worlds, so the world from which our observed data comes from, and we would like to use this data with some clever adjustments to move to some counterfactual world where something desirable has taken place. So for example, the treatment assignment is randomized, which then means we could use this counterfactual world to answer cause-effect questions because we got rid of spurious confounding stuff. And so similarly, inspired by that kind of view, we could think of algorithmic fair inference as moving from a world that's unfair to another world that's fair, where something good happens for us, okay? Okay, so that's feature number one. And I think lots of approaches to fairness think of it that way, I would say, these days. So the second feature of our approach is we think of discrimination. I mean, it's not necessarily about discrimination, although we will concentrate on discrimination to motivate this. It could just be other forms of unfairness. But it's about the fact that a sensitive feature is causally influencing the outcome through some paths we don't want it to influence by. And I'm going to give some examples of that. The third feature of our approach is that what counts as an unfair causal path is a domain-specific issue. In other words, what that means is we can think about a causal model. I think about causal models using graphs. So I can construct a graph, and I could have a treatment A, sensitive feature A and an outcome Y and some paths. And then deciding on what paths are bad in some sense has nothing to do with the graph itself. And this is related to a very old idea by a gentleman named Hume. We all, potential outcome people, we all use Hume's definition of causality, the counterfactual definition. But the other thing he said is you can get a node from an is. And so a causal model just describes some state of affairs, and what paths are bad describes what we don't want kind of morally. And I think it's not so easy to construct a connection there, in my view. So our view is that it's not the job of the causal inference analyst to figure out what unfair is. It's the job of the public debating in the public square to decide this. And I'm going to give some examples where I think there is sort of this intuition that some paths should not be used. Okay. And so the fair world for us, given all of these features, is that it's a counterfactual world in some sense closer to ours with no impermissible path-specific effect. So no effect along the paths we decided are bad. Okay, so we'll get back to 2 and 3 in a bit. And one, as I said, one is common to many approaches. So in the United States, we have the Civil Rights Act and certain other subsequent legislation that forbids employment discrimination and other forms of discrimination based on various sensitive features. If we're given data on people with some covariate sex and some sensitive features such as race or gender and a hiring decision, why? How would we check for discrimination? And of course, this is a live issue, right? Because this is illegal. And one of the interesting things I've discovered trying to read the legislation and subsequent legal commentary on this is actually, they forbid discrimination without technically defining what it is. And I thought that's sort of interesting. I think there are some guidelines for simple summary statistics you can check to suggest that discrimination takes place. Like there are various rules of thumb, but I don't think there is a formal definition there, which I thought was quite interesting. And I think one of the open issues as data scientists can address is try to engage with the legal profession to think about that basically and see if this could be clarified. But okay, so the intuition is one intuitive way to think about this that people have actually implemented is construct a pilot study where you randomly switch the perception of gender on the resume. And the reason you can do that is because if I'm just looking at a resume, I don't actually meet the applicant in person. I just see that the reference letters use pronouns he or pronouns she, and also the name is male name or female name. So those could be switched without affecting the substantive content of the resume at all. So in this particular case, you could do an intervention that switches gender perception. Of course, switching gender itself is not easily possible, but in this case, it's fairly easy to implement. The important thing is you only switch gender perception. You don't actually switch substantive content of the resume. And so the intuition is if you see a difference in hiring rates on the basis of the switch, then there is a problem. And so the way to think about that for a causal inference person is there is some complicated high dimensional thing called gender, because gender is complicated, but a component of gender is perception by the person looking at the resume. And that component better not have a direct influence in the hiring decision. Otherwise, we have a problem because we should be judging people by their accomplishments, right? So that's the intuition. So this is a very famous quote. Yuda Pearl uses this quote in his book to motivate mediation analysis itself, not just mediation analysis for fairness, but just thinking about pathways. And this is just a counterfactual view of how to think about discrimination from a particular opinion, judicial opinion. And this just says the central question in any employment discrimination case is whether the employer would have taken, that's a counterfactual connective would have taken the same action had the employee been of a different race and so on, and everything else had been the same. So this is clearly describing a hypothetical situation that we could encode with potential outcomes or with interventions. And so this is just a brief review of mediation, which is how we think about kind of direct and indirect effects if you want to think about these kinds of had counterfactuals or interventions if you don't like counterfactuals. So we have some data from the observed distribution. We have pre-treatment covariates. We have a treatment A that represents some sensitive feature. We have a mediator or a set of mediators which occur after the treatment causally. And we have the outcome. And we think that M mediates the causal relationship of A and Y. So some of the causal influence goes through M intuitively. And what we want to talk about is this kind of nested counterfactual, which is the outcome, such as hiring decision, had A been assigned to one value, and had the accomplishments, had the mediator been behaving as if the exposure or the treatment was some other value. So in our case, what would be the hiring decision had the gender perception been that of somebody being male, but had their accomplishments been whatever they were in truth? Let's say if this was a female applicant, so that would be A is male, A prime is female. And we can decompose the average causal effect, which is how causal inference people think about the effect of A and Y, into these kinds of two additive components representing indirect effects and direct effects, using these kinds of nested counterfactuals. And as usual in causal inference, if you have this counterfactual parameter, you have to do some work to make sure that it's expressed as a function of the observed data. And in this particular case, under certain assumptions, which I'm going to gloss over, the pure direct effect is a function of the data, specifically this function. You can think of this as a modified G formula where some terms are evaluated at one treatment value and some terms are evaluated at another treatment value. This is also called the mediation formula by Pearl. Okay, so just as a brief aside, there is an alternative way to think about. So the previous slide was just describing kind of the classical view of mediation analysis. This slide describes kind of a more recent view that was pioneered by Robbins and Richardson, I think in 2010, in a paper of theirs. Clarification, what does X represent? X represents pre-treatment covariates. So like confounding factors, things like that. I apologize for not being clear. Okay, so the interventionist approach of mediation goes like this. We have a treatment that's kind of like a vector, and it has multiple components. And some of these components influence subsequent downstream variables, but not others directly. So for example, if A is gender, we could say that M is the content of the resume, and Z is an interviewer opinion of a person. And then both the content of the resume and the interviewer opinion together influence the hiring decision. And we can think that gender is complicated, but it has a component that goes directly into the content of the resume, but not the interviewer opinion. And there is another component that goes directly into interviewer opinion, but not the content of the resume. Okay. And so in reality, in the observed data, these will coincide because, in reality, I am he, him. So AM and AZ correspondingly are that of a male. But you could imagine hypothetically varying only one of them and not the other, and asking what would be the effect if I wiggle only the component of the sensitive feature that pertains to the opinion of the interviewer. And if you find that it's different, then there is a problem. And so that's an alternative way to think about direct effect that's perhaps more intuitive, because it's all about intervention. So there isn't any weird nesting where you conflict the treatment assignment. I just have components of the treatment and I intervene on them. It's a standard intervention. Again, I'm not going to talk much more about this, but we have this whole paper that I have at the end of the slides that discusses how you can think about identification here, which is quite straightforward, and how you could think about encoding more complicated mediation problems in this way. And I think it's very natural for a lot of fairness problems to think about mediation in this way, because very often sensitive features are complicated, like race or gender. And it's very natural to think about components that go into different subsequent variables, basically. So I find that quite natural, but I'm not going to get into this more for lack of time. So I'm just going to talk about standard mediation for now. Okay, so our...
Hi, Ilya.
Yes.
Sorry to interrupt. Here is a very quick clarification question. Here, does N represent the perceived content of the resume?
Yeah, it's whatever the interviewer reads. So the thought in the thought experiment, it's kind of like the way Hopkins does graduate admissions. They give us a CV. We look at this CV. That's all we look at, just a PDF of the curriculum vitae. And on the basis of this, we make some decisions, like do we invite somebody for an on-campus interview? So it's whatever we perceive. Yeah.
Thanks.
Sorry, I didn't see this follow-up. Okay, so more formally, the approach goes like this. We have the observed data distribution with covariates, treatment, mediator, and outcome. This was induced by some causal model. We want to predict, for now, let's say we want to do prediction problems. So we want to predict the outcome from these features in a fair way. So we have a causal model. We're going to think about a graphical causal model because we find that helpful. We consider in this graphical causal model all causal pathways from A to Y. And then we decide what the bad ones are. And in doing so, we don't just do it ourselves. We consult with somebody who knows the domain and who can tell us that. So in the context of hiring, for example, it's definitely bad that there's potentially a bad influence of perceived gender or race on the hiring decision. That I feel like that shouldn't happen, and I think most people will agree with me. However, it could be that some indirect paths are also bad because life is complicated. There's structural unfairness, and the fact that somebody is of a particular race or gender may meant that they had structural disadvantage in their life, which meant that their resume content is less favorable compared to somebody of a different race or gender. And that could potentially be also taken into account. I'm just not getting into this in the interest of time. I'm just saying that this is a complicated question. And it's definitely not something that's for us causal inference analysts alone to decide. Okay. So in whatever way we decide what the bad ones are, for the interest of illustration, we'll only talk about the direct one being bad. But this is not an essential feature of this approach at all. So then we compute the pure direct effect as a stand-in for the fact that there is potentially a problem. And the sense in which there is a problem is if we were to run, remember this pure direct effect kind of like mimics that name switching study. So in context where these kinds of name switching studies where I change the perception of the sensitive feature but keep the substantive features the same, if we do such a study and we see that there is a problem, then we think there is discrimination. And so we translate that to saying that if we didn't run this study and we used observed data to predict what would have happened if we did such a study, that would sort of imply some sort of problem. Sorry, when I say to fix, I just mean we decide what paths are bad. And in subsequent analysis, we're going to make it so that the causal effect along those paths goes away. That's what I mean. I don't mean fix like intervene, I mean fix like in mathematics, like consider these paths. Okay, great. So if the direct effect is not zero, then in a certain sense of this kind of name switching study, we are unfair. We are making decisions inappropriately on the basis of a sensitive feature. And so what we want to do is we want to find a fair world that's close to the world we actually see, but where this direct effect is zero. Now, there are lots of things you can already say here, like the fact that the direct effect is an expectation. So it's some population aggregate, and we might want to be something, say something more individual, like maybe for certain kinds of people, we want it to be zero as well, or we can talk about other kinds of effects. And of course, there's lots of fairness papers with lots of criteria we could potentially make zero. So I'm going to leave all of that aside for now. So in what sense can we be close? Well, we'll be close in the KL sense because we're going to think about this in terms of likelihoods, and I'm going to get into why that is. And I think that's open to critique as well. I think as Ricardo will talk about. So, okay, so the way we would do it with actual data is we have some data from a distribution that corresponds to a causal model. We have some estimator for the direct effect that we could use. So we would like to do a constraint optimization problem where we maximize the likelihood subject to the constraint that the effect as given by this estimator is close to as null, which could be 1 or 0 depending on the scale. And here we have epsilons just because we wanted to give people the option to trade off how little they want this effect to be versus the complication of solving this actual problem, because we find that constraint optimization problems are not so easy to solve actually. And sometimes you would be willing to tolerate a little bit, or potentially we're willing to tolerate a very small effect in exchange for much better performance of the ultimate predictor we're going to build. Now, of course, because we're using a particular estimator, estimators use different parts of the likelihood depending on the estimator you choose. So what we constrain will depend on the estimator, of course. Now, the point of view that we take, which not everybody takes, is that we start with the world and we move this entire world to be fair, to be P star. And therefore, anything we do after that has to live in that new fair world. In particular, a lot of prediction problems, the way they work is you have some training data, you train a predictor, and then some new data comes in, and you want to use your predictor to do a good job on this new data you haven't seen before. The important thing about that is that this new data doesn't come from a fair world, because it probably, like if you're doing standard like classical prediction problems, my training data is from distribution P, and my new samples I haven't seen before are also from distribution P, although of course not necessary. But the point is neither P, P from which test and training data, even in this classical case, comes from, isn't fair in our sense. And we want to move the whole problem to be fair, including new instances. And so what that means is if a new instance comes in, so some person comes in with X, A, and M, that came from the marginal P, which isn't fair. And so because we want to move the entire problem to be fair, what we do is we end up marginalizing over everything that was constrained. So for example, if we use an estimator, like a G-formula estimator, the plugin estimator that uses the outcome and the mediator, we don't have the outcome in a new instance, but we do have the mediator. And because the mediator distribution was constrained, what we end up doing is we end up aggregating this person over the distribution that we learned in the fair world. So effectively, we're selectively forgetting something about this new person because that's the price we pay for making sure that as we get new instances and we make decisions on them, the overall, if I think about the distribution of new instances, that new distribution still maintains this property that the direct effect is 0. If we didn't do that, the direct effect would still be there. What is the accuracy cost of fairness? So you will be less accurate. So I'm going to get to that just as I had a quick illustration slide about this. You're going to pay a cost for this. It's hard to say what that cost will be in general. So we'll get to that in a little while. So Compass is this it was this model that they developed for predicting recidivism, and recidivism is important because if somebody is out on bail and they commit a crime again, that looks really, really bad for the person who made that decision. So very often people are quite conservative in these decisions, and they thought that they could use a regression model to try to get a handle on the kinds of people who would be dangerous to release. And so ProPublica has a very famous expose on the use of this model. And of course, this model does not use race directly, but of course, the fact that it doesn't use race directly, if you think about causal pathways, doesn't actually help. Let me give you an example. So I live in Baltimore City. Baltimore City is a very segregated city because of history of zoning laws that excluded African Americans and Jews from settling in certain neighborhoods. And these were in the books until the 60s, so in living memory. So if you look at Baltimore neighborhoods by race, it's quite segregated, actually. And even if you don't use race, you may inadvertently use something like zip code. And zip code in a city like Baltimore is a very good proxy for race. And more generally, if you don't use race, all you're saying is I'm going to marginalize over race. The fact of the matter is race is still a thing, and race is influencing downstream variables, like how much attention from police you get. So the fact that you've marginalized over race doesn't change the fact that the causal pathway is still operating. So I think dropping race doesn't actually accomplish anything if those are the kinds of things we're worried about, right? The improper causal influence of the sensitive feature, okay? Okay, so this is just an illustration. This is not a serious analysis of this ProPublica data because we didn't get the data from Compass, rather. This is just an illustrating the answer to this earlier question in chat. So here, Y is recidivism, A is race, which we're going to assume isn't influenced by other covariates, although we can talk about that. M is conviction history as defined in some way, and X is other demographics. So here we're using a log ratio scale pure direct effect, which sort of intersects null, but it's sort of there to some extent. And so this is just an illustration of the sort of predictive performance we could expect to get. So this data wasn't very good, so we couldn't get we could do a bit better than random, but not very well. And so one thing we could do is we could just do the naive thing and just predict the outcomes that we were able to define on the basis of everything, including race and conviction history and demographics, and then we get some accuracy. The other thing we could do is we could just marginalize out race. And then, of course, we will pay a price for that because race is potentially informative in the sense of predictive accuracy, right? And the other thing we can do is we could marginalize race in a particular way and marginalize the mediator conviction history because of the fact that we're constraining the direct effect and the models that we used were constrained. And so consequently, any new person that we use to predict on cannot use those features directly. And the point is, if you do that, you could still get reasonable accuracy. You could even beat the predictor that just drops race entirely but uses M. At least it did in this particular case. But you will never be able to outperform a predictor that uses everything, because you're not using data as effectively as you possibly could. Because one of the things you're doing is you're kind of operating with one hand tied behind your back, because you have to make sure that some direct effect is zero. This is a well-known thing. There's been many papers in fairness that say that there are negative results, that if there are multiple criteria, they cannot simultaneously be satisfied, or if you want to minimize a particular loss, you cannot do that all the way if you also want to satisfy some other criterion. So this is not very surprising, right? Because you're constraining how much information you're allowed to use. In this, I mean, you could look at the details of this kind of illustration in our paper. We used a particular way to constrain the PD using sampling, essentially. And the point is that there is no hope to beat, if we're in kind of parametric land, or if we know the model exactly, there is no hope to beat maximizing the loss directly, basically. I will take that question at the end, if that's okay. Okay. All right. So this is just an illustration of the kind of thing you will do. So you can still do a reasonable job, but you will do less well than just a straight predictor that ignores fairness issues entirely. And so our take here is that fairness is a hard constraint, and we have to satisfy it, and we have to do as well as possible while satisfying it. And that's because we just want to translate the entire problem in a fair world and then do the optimal thing in that world. So that's the point of view. That's not the point of view that everybody else have. The other thing you can do is you can try to trade off accuracy and fairness in some way. Okay, so that was the basic setup from a couple of years ago. And there are a number of ways you can extend this. One of them is learning policies. So in policy learning, in off-policy or enforcement learning, if you like, what we do is we have a sensitive feature, we'll now call it S instead of A, and we have a decision that we could make on the basis of pre-decision variables, potentially including the sensitive feature. And this decision is made in such a way that we want to, for example, maximize expected utility. So let's say maximize expected outcome Y. And you could try to do this online, which is what reinforcement learning people do, or you could do this retrospectively, where you have a data set, and in this data set, some decision rule for A was followed, and we want to see if we could do a better job than a decision rule that's followed. Very often in healthcare, this happens. Like you have a particular, clinical policy, and you want to see if the clinical policy could be improved, that sort of thing. And then that problem, you have your data set, you're not allowed to generate anymore, which is very different from the online reinforcement learning setting. So in the potential outcome notation, what we want to do is we want to think about the potential outcome for Y. Had I set A according to some function of the pre-A covariates, F, and then we want to optimize over F. So it's a combination of a causal inference problem where we want to figure out the utility counterfactually and then optimize on the basis of this utility over the F. And there is a very, very big literature that I can't get into on these kinds of problems. And remember, this is a fairness talk, so we want to think about these kinds of problems fairly. And I think when we started thinking about it, we realized that it's kind of a can of worms as well in terms of the kinds of biases that can arise. Bias is very overused, so we're trying to be precise when we use that word. Of course, in causal inference, we worry about confounding bias and model misspecification. So confounding bias we'll talk about later is if I don't measure all the covariates for A, I'm potentially not identified and I have to use tricks, basically. And model misspecification is if I use like an outcome regression or a propensity score and I get the model wrong, then I have some problems from that. So everybody who does causal inference deals with these issues, and people have these doubly robust estimators to deal with this, and they have confounding tricks and so on. So because our fairness criterion is about the direct effect, we also have to deal with this because we have to make sure that our criterion is even identified from the observed data. And confounding bias is a threat to that, right? As is model misspecification. If we get the model wrong, our assessment of how much discrimination there is going to be in jeopardy, right? And in the context of policy learning, there are other problems. One of them is, of course, retrospective bias, which is that we have our data, we look at our data, and in our data, the direct effect is there. So this is like, policing in Baltimore City is somehow systematically racist because police only go to certain neighborhoods, and it's primarily people of color who live there. And that will show up basically, even if those people are, less likely, are as likely to commit crimes as somebody in a different neighborhood. It's just that the police happen to be present in that neighborhood, right? So this is kind of like your criminal record would be bigger than it would otherwise be for no good reason, essentially. That's an example of retrospective bias. And so I think a lot of approaches to fairness, including causal ones, deal with retrospective bias. In the context of policy learning specifically, there is this worry of perspective bias, where even where it could be that the policy creates problems. Now, in observed data, some policy is followed, and it's perfectly logical. It's logically coherent to imagine a fair world already, where a policy was followed that completely doesn't have any kind of discriminatory issues. Like, let's say you just flip a coin or something like that. And it's possible that if you want to, in your quest to maximize expected utility, you could introduce bias. So, for example, I am a judge, and I decide on bail decisions, and I look at a person's skin color only, and I just decide if they should be released on bail just on the basis of skin color. So that's an example of, even if there was no kind of discriminatory bias before, an actor creating a policy could introduce this. And this is, I mean, I'm almost certain this happens, right, in reality. And if you're trying to come up with a utility maximizing policy, that's a different bias you have to deal with. And the thing to understand is this is different from retrospective bias. Each one of these could occur independently, or they could occur together, right? Okay. Okay, so I think longer questions I'm going to leave for the end, because I don't want to stop for too long. Okay. And the particular worry, of course, is the cycle of injustice. So, like, there is something that's unfair, and then these decisions get made, and it perpetuates the unfairness in some way. And so this is a lot of people who worry about social justice. That's what they worry about, right? Okay, so we're going to have an approach, but I think, like, I think the most important thing about this policy part of the talk is just the fact that these orthogonal sources of bias exist. And I think when you think about decision-making in this way, where you reify the decision, it's important to think about them kind of in isolation. Well, I certainly don't claim that what we did is the last word on this. So, okay, so in the interest of simplicity, remember the graph we have S now, and we have A. And so I think now we'll say, let's say that we don't want the effect of S and A not through the mediator, and the effect S and Y not through the mediator also. So now there are two things. There's the decision and the outcome. And let's say now we don't want the direct effect on either. And those are, so if I write down those effects, I could think about them like this as a nested counterfactual. I can also reformulate these in the interventionist mediation approach with components of S, but I won't do that for time. And the key idea is there are lots of semi-parametric estimators that some of them don't use Y, because typically we don't have control of Y, which is good. And some of them don't use A, which is also good, because A is the policy we're trying to change. We're trying to change how A is determined in terms of treatment variables. So what we could use the M and S models. And remember, what's constrained is the models that we choose for our estimator. And in this case, you could use an inverse weighted estimator for both of these that uses M and S models precisely. We could constrain those models and construct our P-star distribution from that. And the important thing about that is we have a new distribution, kind of P tilde, that constrains two distributions. And in this distribution, we don't need to worry about Y because it's not set by us. And we also are allowed to set A arbitrarily according to the policy, because we've already ensured that the direct effect, at least as quantified by S and M, is 0, regardless of what we choose. So this is a bit of a trick. The other thing that we could have done is we could have used an estimator that uses A, but then when we chose the policy, we had to make sure that the policy optimization problem was constrained such that whatever policy we chose, the overall effect that uses that policy is still 0, which is a much harder problem, so we chose not to do it. Okay, and so we can then maximize. So in the way we did it, which was a bit of a trick, we could maximize F just in an unconstrained way, because constrained problem was already done for us. And of course, for people who learn policies using retrospective data, you could use Q-learning, G-estimation, value search, regret minimization. There are lots of approaches. We implemented some of them. You can check the paper for details, but I'll just discuss Q-learning to fix the ideas. For a single time point case, the Q function is just the outcome regression under the settings of pre-outcome variables. And the optimal policy simply chooses A to maximize this function for any value of inputs, provided, of course, that the Q function was specified correctly. And again, because we want the mindset is we want to move the entire problem to a fair world, so we cannot adapt the resulting policy to new instances directly because we must work within this tilde distribution. And the usual thing we do is we marginalize over stuff we used. In particular, if we used S and M, we just end up marginalizing the Q function over that, and we just end up using X instead, which is it's kind of the policy learning analog of what we did for predictors. And you might ask, well, why are you marginalizing over things? Because you're losing information. And our answer is, again, the way we're thinking about the problem is we want to do the problem in the fair world. So that translates directly to us just imposing this direct effect to 0 as a hard constraint, essentially. Okay, again, this is an illustration. This is not a serious analysis. This is the sort of thing that you can expect. So here we restricted our attention to African-American and Caucasian cohorts in the COMPASS data. There are some variables on demographics, past convictions, and recidivism in the past 2 years. So what we did is, so the way COMPASS works is it gives a score, which is, I think, from 1 to 10. And, higher scores means the person is more dangerous somehow. So here we binarized it because we're doing a binary release or keep in jail decision. And so we have low scores and high risk scores. And we define the utility function parameterized by this theta. And what theta says is it tries to quantify that there is a trade-off. So a priori, it's bad to keep people in jail. So you pay a penalty if you keep a person in jail. However, it's really, really bad if you release somebody and they commit another crime, and they recidivate. So in other words, the way that this, and then theta trade basically governs how much you trade off one versus the other. And the point is, this is incentivizing you to, if there is no good reason, release a person, but if this person seems very dangerous, don't release them. Okay. So what you can see from this plot, again, this is just an illustrative plot. The sort of thing you see is that if theta is very low, you basically release everybody, so incarceration rate is 0. As the utility parameter grows, eventually you decide that certain people have to be kept. If you don't constrain the policy you learn in any way, you will end up many more African Americans being incarcerated. Of course, if you end up constraining the direct effect in the way that we've discussed, the difference shrinks, but it's still there. I suspect because the data is not very good, and I suspect because paths not through the mediator are potentially also unfair, which is something we didn't get into, because remember, this was just for purposes of illustration. We only talked about the direct effect of race on the decision and the outcome. So that's the sort of things you should expect to see. And I think there are lots of hard questions about to what extent the differences, racial disparities are there for a reason that makes sense or not. And almost certainly a lot of this should disappear and has to do with historically unjust policing and all sorts of lack of economic opportunity, all sorts of other things that it's really outside the scope of this talk. Okay. Oh, tilde just means it's a distribution that we construct that's constrained such that the direct effect is eliminated in a particular sense. It's to contrast with P, which is the observed data distribution. Okay, so a lot of these problems, so I'm hoping that this part of the talk will be helpful just for causal folks who want to use causal parameters as constraints. So typical learning problems, if you want to constrain the causal parameter, is you maximize some loss. In our case, we want to maximize the likelihood, or minimize the loss, maximize the likelihood. Subject to some constraint, the constraint is a moment constraint. In this case, this is the usual direct effect that's identified by the mediation formula being 0. It's very hard to do these kinds of problems because it's an annoying parameter that we want to be 0, because it's a function of all these nuisance models that are high dimensional. And what you can do is you could use a trick I learned from Jamie Robbins that structural nested models are based on. And the idea is you reparameterize the observed data likelihood, so the direct effect is a parameter that lives in the likelihood. And this is the way you do it. This is a trick that Jamie came up with. He did it originally for covariate adjustment and total effects, but you could do it for mediation. So what you do is you look at the outcome regression and you point out that you could write the outcome regression as this weird object. And the reason this object is weird is it has this f function inside of it. And this f function is this kind of blip function for the outcome. And you have to integrate it with respect to the mediator. So what ends up happening is you end up writing your outcome regression in a variationally dependent way that also depends on the mediator model. So variational dependence is fine. It just complicates fitting a little bit. But the advantage of doing it this way, so it is a slightly weird way of doing it, but the advantage that you get is that you have this phi in there. And you could think of this phi for a binary A as the direct effect. So what that means is that you can write down your likelihood by just chain ruling, including this outcome regression model. And in your likelihood, there is a direct effect parameter directly encoded. And the reason this is nice is if you want to do constraint maximum likelihood such that you want this parameter to be 0, you can just do it as a box constraint on this parameter. The price you pay is you have variational dependence, so the fitting is a little bit more complicated. And my former student Razi, who is now at Emory, who is of course involved in a lot of these papers, derived this kind of trick for many, many path-specific effects that you might want to do for these kinds of problems. Okay, so the other thing that we can do is the usual setup for prediction problem is you have training data and you have the test data that you haven't seen before. You want to do well there. But another way to think about it is think about the prediction problem retrospectively, where you have your data set. So this is the way causal inference people typically think. I have a data set. I want to do a good job on this data set, and that's it. I'm not trying to do generalization. So, I have a cohort. I'm making some predictions for this cohort, and then these predictions are going to be used for the decision maker on this cohort. It's no out of sample stuff. Okay. So in that case, because of our worldview, we want to move our observed data to the fair world, we could move the entire world, the entire distribution there. Previously, we kept some of this distribution unconstrained, specifically pre-treatment covariates X, because we wanted to use those to predict in instances we haven't seen before. But now we're no longer concerned about that. We're just concerned about constructing an entirely new distribution that is close to the new distribution, where we're allowed to constrain absolutely everything. And one way to think about it is using empirical likelihood methods. And so the way that works is you write down kind of a semi-parametric likelihood where you have pieces that are completely non-parametric. So they're just weights, one weight per row. And you have either parametric or semi-parametric pieces for the variables of interest that are not covariates, like the treatment, the mediator, and the outcome. And you want to maximize this kind of likelihood subject to the property that you have, the weights add up to 1, kind of like the empirical is 1 over n, so that adds up to, trivially. So you might want to change those weights to make sure that some constraint is satisfied. And typically they think about moment constraints, which is great for us because a lot of these causal effect being 0 constraints can be viewed as moment constraints, right? And you could solve this. There are Lagrange multiplier methods to do this kinds of problem that you could learn about in Owens's books and more recent papers. And just to illustrate how that would work, we just did a simulation study. So we have a clear paper on this not too long ago, but you could read about it. And what we were comparing is the unconstrained model, where you just used unconstrained maximum likelihood, and then we constrained the maximum likelihood in the way described at the very beginning of this talk. Then we constrained the model by doing box constraints, and then we did this hybrid likelihood. And then we could also combine this hybrid likelihood with EL ideas with reparameterization. And as you can see, what ends up happening is the unconstrained likelihood is the closest to the true data generating process, and it has the best error on the outcomes. But it has the direct effect, and all of these other methods are able to essentially eliminate the effect to the tolerance desired at the price that they're further out from the true distribution, which makes sense. And the ability to constrain the entire distribution, including the pretreatment covariate distribution, allows you to kind of do a better job on making sure that your outcomes are not too different from the unconstrained world, which is important in these kinds of retrospective cases.
Sorry, Ilya, can you wrap up the talk in the next few minutes?
Oh, sure. Yeah. So I'm going to just briefly, I'm just going to very briefly mention proximal. The obvious problem with a lot of this stuff is that it assumes that things are identified because you have enough covariates. In practice, you have unobserved confounding. That's certainly true for the average causal effect. So in this particular case, the average causal effect is not identified, and it's certainly true for mediation problems. And there are lots of tricks that people have used for discovering how to adjust for unobserved confounding in the right way. And there is a new class of tricks called proximal causal learning that is based on non-parametric IV stuff that was developed by Eric Chetkin and colleagues. And the way it works is it assumes that there are certain proxies, in this case, Z and W of the unobserved covariate. And there are certain independence assumptions that you can kind of show on this graph, and certain completeness conditions that allows you to essentially identify the average causal effect by using a certain bridge function that uses these proxies instead of the underlying confounder. And you get essentially a version of the G formula where you adjust for covariates, but instead of the outcome regression, you use this bridge function instead. And there are, because I have to finish this talk, I had some more slides that I'll skip, but essentially this idea is very general. It applies to lots of causal parameters with unobserved confounders, including for mediation. And I have some paper links at the end of this talk that describe how we do this for mediation and how we could do fairness problems in this way. Okay, so to conclude, I've described an approach to fair inference based on mediation because in this approach, we want to get rid of unfair causal pathways, the way the treatment that's a sensitive feature influences the outcome. There are some justifications for this approach. It's not an arbitrary approach based on certain kinds of views on discrimination and other kinds of unfairness that can arise. If you think about this parametrically, we get a constraint optimization problem, which is a very hard problem in general. If we use empirical likelihood methods, we can constrain the whole joint as long as we don't care about out-of-sample prediction stuff. Likelihood reparameterizations are a very general trick that Jamie Robbins came up with that allow us to constrain causal parameters in a way that just reduces to box constraints, which is quite nice. If we have unobserved confounding, we need new identification theory to deal with this, and proximal causal learning is a great way to think about that. Many open problems, ongoing work on health disparities, of course, by many people, including me. And there's evidence that prediction models in use may be quite discriminatory in our sense. And that's it. So here are the relevant papers. Feel free to check them out on mediation, on fairness, and on proximal inference. And I would like to gratefully acknowledge my funders. And that's it. Thank you. Hopefully I didn't run too over. Thank you.
Yeah, thank you, Ilya. That was great. And in the interest of time, let's move to our discussion. Ricardo, are you ready to share your?
Yes, I'll share my screen. Can you see this well?
Yes.
All right. Thank you very much for inviting me for the discussion, this fantastic line of work by Ilya. So what have you learned here? Of course, as you might expect, we do have something to say as causality being a useful concept to operationalize fairness. And in particular, the ways we divide the input, which is very clear in Ilya's talk, is thinking about the model of the world and value judgments about what is fair or not. It's important to make this distinction something which is provided to the method, because here nobody's attempted to mechanize value judgments. They involve ethical calls, for example. It's not really the role of a purely synthetic derivation of a causal model into value judgments that is the point of this work. And sometimes it's good to see something like Ilya's method be presenting this clearly, because it does get sometimes confusing for people who's coming from outside to understand what their goal at the end of the day is, to make use of value judgments, not to derive them. And also, I like very much the ways that were formulated in terms of linking to work on parameterizations and fitting models on the constraints, and particularly the more recent work on how to deal with a measure confounding via proxies. These are all important points as take-home lessons for people who are thinking how to make use of these models. But I think the discussion will be particularly interesting in terms of the more foundational aspects, what it means to deal with fairness in causal models and what you gain by that. Okay, so I present here a lot of different ideas. It's kind of half-baked, but hopefully will be good to tickle your brain and think of other issues that may be related to what you just saw in Ilya's talk. In the problem framing, it was very nice to have this distinction between prediction problems and policy problems to make sure everybody's on seeing the big picture. There are, of course, many other methods that were not, many other problems that were not mentioned. They are very mainstream in fairness that are not quite still the role of causal inference. Maybe some of you can think of ways of linking that. That include problems of representativeness, for example. If you want to present information to a user via search engine or recommender system, you want to also think about diversity questions on the background of the providers of their content, for instance. But these are just ways of illustrating that there is a lot going on in fairness that is not necessarily the case that causal inference has a very much to say in those regards. Okay, so in terms of the framing, as I mentioned, it's nice that you have these clear-cut inputs that come from outside, come from knowledge about the domain. But it's good also to consider which are the kind of inputs you could make use of, like loss functions, for instance. Because likelihood loss, which was the one that was particularly exploited in this work, is a specific type of prediction loss. And often we have actually in real world problems have more than one stakeholder, or more than one entity that is affected by the decisions. And sometimes loss functions needs to be explicitly designed so that you understand what the trade-offs are. So to give you a completely hypothetical scenario here, consider this case that is somebody from a minority background is applying for a loan. You want to start a business, that the bank decides that by looking at the business plan. And there's a predictive model that says, well, there's some probability of defaulting on this loan or not. And the model says, well, is that a very high probability according to our standards, and maybe should decline the loan, which is good for the applicant, because you don't want the applicant to fail, right? There's a cost that the applicant will pay, even if they try to start their business and they fail on that. Now, one thing that you may think about, of course, is these methods are probabilistic. These predictions can be probabilistic because they have a high risk of failing. It's not a given. There's no fatalistic consequence of trying to start a business and being destined to fail. It doesn't work like that. And one thing you can think about is if you were to ignore this discriminatory context that gives your predictor the calibrated risk of failure, if you were to ignore that, a predictor would maybe flag as a sound investment, you would go ahead. So maybe the thing to do there is trying to really take into consideration which kind of losses you have that maybe in a more idealized world would be able to ignore information that is discriminatory, model what is going to happen if you just ignore this information, there's some links to privacy there, and maybe think about the loss in terms of how it affects different stakeholders. What we have, for example, the burden doesn't fall completely on the shoulders of the applicant in case the default takes place, but it's shared among bank or maybe among a society via some particular grant scheme. You could still think of the causal model there, providing a framework, not necessarily about what a fair world should be about, but which kind of information should be actually used in an optimized prediction problem under a particular loss. So linking more directly to the issue of thinking about not what ideal world would be like, but think about a predictor using only particular subsets of information. So if thinking about the design of a fair predictor and less about what the world will be under changes to it, they make it more clearly linked to the loss function. So one way of understanding this, if you think about maybe the model for the actual outcome is not something that's at play here because you're not really interfering with it. What we are doing is creating a predictor, some sort of Y star, which is not the same thing as the outcome Y. You control Y star, you don't control Y. So one way of interpreting the problem is how you design Y star. And you can think of the same framework that Ilya presented as putting constraints on the predictor directly, think just about the predictor itself. But this would affect the kind of causal graph you're thinking of. We think about a causal graph that explicitly uses Y star, and sometimes this makes sense if you think about, for instance, a situation where your label Y and your sensitive attribute A are not linked in a causal direction. They're just confounded, for example. May think that it's fair game to use the protected attribute. But if you think about A as an input to a prediction Y star, like in this bottom right diagram, maybe you think differently. Think about that A here should not be used directly because it's affecting the prediction you're making. And in the moment you separate these, maybe just think of Y as this extra information that is used to calibrate the loss. But we think about constructing a Y star in the way that the real label plays a role is in terms of defining what empirical loss would be without any particular exploitation. It's model per se. This is P of Y even varies. In terms of policy making, I mean, one way to think about it is again just in terms of what happens under the distribution of the real world, but the way you are interfering on it is how you design your policy A, how you define how your actions A are generated. Maybe the ultimate goal should be directly trying to mitigate real world unwanted disparities by seeing what is it you can do by trying different policies and see how the rewards behave as average over the real world distribution. So it's not totally clear to me what is this that he gained by having this detour into imagining what a parallel fair world would look like. Because one direct way of thinking about it is instead of modifying the distribution of M&S, well, they are what they are, right? I mean, when you think about rewards in the real world, you're going to follow this distribution. One thing you can think of is the only thing we're going to influence is the design of A. So it's still everything based on the distribution of the real world associations between X, S, M, and Y. And you're constrained by what you can do. You will be able to use maybe historical data to do off-policy learning. But if you think if you want to change the distribution of A or distribution of actions to what extent you can mitigate some of the unwanted effects you have. Maybe you cannot do much because you're constrained by a pre-existing choice of action and a pre-existing support distribution that doesn't allow you to deviate much from the status quo. But hopefully will be some sort of improvement you can make this. You can make, for example, that there is less disparity on Y being the number of people who get to college from different schools that have different racial backgrounds. Being having a smaller gap, somehow it changes the structure of some learning resources you distribute as encoded by A. Okay, and finally, just to wrap up, I did mention there's very nice that this distinction between prediction policy, but sometimes of course blurred because a decision that you're predicting will be used down the line to change some process. So if you're doing shortlisting for people to be interviewed, to change the way who gets to be predicted as a promising candidate, of course, this will have implications down the line. But this also take into account what's the nature of this quantity you want to predict, because you can think of those Y variables as the actual decisions that have been logged, who gets shortlisted or not. But then it gets a bit strange when trying to use this to calibrate your future predictions because you don't trust these decisions to begin with. Maybe a more reliable type of prediction problem to think about is which kind of desirable features this person will be shortlisted for getting college would have. So maybe this person happens to graduate. You're trying to do a college admission process. You don't try to predict what would be the decision based on historical data about what would be the performance of that student, and then create your own decision protocol based on this prediction. And the reason why I mentioned this is because it raises other problems that may be relevant for causal inference. Because of course you try to say you should give a college position to someone who will graduate. You don't only know this for people who are selecting the test, right? You don't get to see this outcome for people who are not previously given a chance. So there are other issues there that may involve sample selection bias. With this that you can do to take into account that you have this misinformation, or maybe there's something that you can do a particular special cases of the problem, such decisions at the boundaries, which are as good as randomized. It matters more like regression continuity design could play a role on that. Okay, so this is basically what I want to add to the discussion here. Many thanks to Ilya, who's been a card-carrying person from the very beginning in terms of uses of causal inference in modern algorithm fairness. Has been there from the beginning of that. So you should really be thankful to the attention that causal inference gets in terms of contribution to fairness, in good part due to this work by Ilya and his collaborators. I'm looking for what other ways of play with that. I was particularly intrigued by this throwaway comment about intervention notions of mediation that may be interesting new direction for the type of work he's doing here. Right. Thank you very much.
Yeah, thank you, Ricardo. We're very over time now, but Ilya, do you want to take just 1 minute to respond?
Yeah, I'll just say two brief things. The first is, I mean, I think about mediation in an interventionist way. I chose not to present most of the talk that way just because in the papers it was presented kind of the classical way. But I think the interventionist way is much more reasonable for a lot of these sensitive feature problems. The other thing I wanted to respond to is the why likelihoods question. And I think it's because I'm confused and I don't know what else to do. And I think the reason is in fairness problems, there is the primary thing of interest, like a policy optimization or a predictor, which, you know, imposes some restrictions, like, you know, some inductive bias on your problem. But you also have the separate thing, which is some effect you want to be zero, which imposes its own models that you need to estimate the effect. And I think it seemed important to me that these be coherent. And if I have a likelihood, then everything is coherent. I'm using the likelihood for prediction and I'm using the likelihood for estimating effects. So there is no problem conceptually. And I think if one doesn't want to use the likelihood, because I think it's very sensible to use other losses. Like I'm doing prediction, I want to minimize the risk of catastrophe, so it's some other kind of loss, right? Not the squared loss. So that's very reasonable to do. But I think it's important to make sure that there isn't incongeniality basically in your procedure. And I'm frankly not sure how to think about that to this day, which is why we proposed the likelihood. It wasn't out of any you know, like we didn't think it was fundamental to thinking about fairness in any way. It was just a way to make the whole thing statistically coherent. So that's kind of my answer to you. Maybe that's not a very good one. That's all I have to say. I think Ricardo said a lot. I probably don't have time to address all of it. I think I'll take it to email.
Yeah, great. Thank you, Ilya, for the very nice talk, and Ricardo for the great discussion. So I just wrap up with just a preview of next week's seminar would be by Maurice Hart from Max Planck Institute for Intelligent Systems. And I'll see you all next week.